Okay, let's unpack this. Have you ever, paused to really look at a building and think about how all the essential stuff gets in and out? The pipes, the wires.
Hmm.
Sometimes you see them running up the side. Other times they just uh, vanish into the ground or the walls. It's something we probably don't notice much, but it's a huge decision engineers make. Overhead, underground, or maybe even inside the structure itself. Today, we're diving deep into that choice.
Yeah, and it's fascinating because it's really not just about how it looks, aesthetics. It's this complex balancing act. It affects how the building works, safety, how
Right.
much it costs to maintain long term, even its sort of environmental impact. We'll get into the key things engineers have to weigh up when they're deciding where to put these vital arteries of a building. We've got some great examples to look at.
And for you listening, our goal here is to sort of pull back the curtain on why these choices get made. We'll touch on things like gravity, water pressure, access for maintenance, insulation, using some real-world scenarios from our research to make it all, click. You'll definitely see buildings a bit differently after this. Right, let's kick things off with electrical systems. That seems like a common place where you first hit this overhead versus underground thing right at the edge of the property. So when a building needs power, what are the basic ways it gets there?
Well, for electrical service, the main choice is between what's called overhead service and underground service. Overhead is probably what most people picture those power lines on poles running above ground, connecting, directly to the building's main electrical panel. It's often simpler, maybe more direct in some situations, kind of the default in many older residential areas.
Okay, so overhead is the visible path, then underground. That just means hidden away,
Yeah.
buried.
Exactly. Underground service means the conductors, the wires, are routed beneath the earth. Now, sometimes they're buried directly, but actually, more often, especially for better protection and, importantly, future access, they're put inside raceways or ducts. Think of those like protective pipes or conduits the wires run through.
Oh, okay, like a pipe within a pipe situation almost.
Sort of, yeah. It protects them. And this brings up a key question for the engineers. Why go to all the extra trouble and, frankly, expensive burying them? It's definitely more work up front.
Good point. It sounds way more involved. So what are the big reasons to go underground?
Well, a major one is protection. Overhead lines, they're vulnerable. Storms, wind, ice, falling trees, power outages happen. They can also get hit by vehicles, things like that. Underground lines are shielded from most of that immediate physical danger. Another big factor is space and aesthetics, especially in dense urban areas.
Right, you wouldn't want wires draped all over skyscrapers.
Exactly. Imagine the visual clutter. It would be a mess. And related to that, you often find things called transformer vaults in cities. These are specially built spaces, often underground, to house those big electrical transformers. It keeps them safe, out of sight, and contains the noise and heat they generate.
So that initial decision right at the property line, it already sets up a lot of complexity before you even get inside the
Yeah.
building. Fascinating. Okay, let's switch gears to water. Probably the most essential utility, right? Getting clean water in, getting wastewater out efficiently. This is where things like gravity, pressure, even the materials used for the pipes themselves become really critical.
Yeah.
Talk us through the drainage side first. What's the main challenge there?
For drainage, gravity is everything. It's non negotiable, really. The absolute core principle is making sure there's a constant downward slope. Water has to flow downhill. If it doesn't, you get backups, clogs, stagnant water, big problems. And another critical piece, something people rarely think about, is managing the air in the system. You need to keep the nasty sewer gases out of the building.
Okay, how does that work?
The only thing standing between those unpleasant, sometimes hazardous gases in the sanitary pipes and the air you breathe inside is a small amount of water held in what's called a fixture trap. You see them under every sink, every toilet that U-shaped bend.
Ah, the U-bend. So it's not just there to catch lost rings.
Hey, well, it can do that too, but its main job is to create a water seal. And for that seal to work properly and stay clean, the trap has to be self-cleaning. That means every time you flush or run the water, it should completely flush out any sediment or gunk. Otherwise, the seal fails or it clogs. Our sources actually get very specific here. These traps usually need a water seal depth between 2 inches, that's about 50 millimeters, and 4 inches, or 100 millimeters.
Wow, that precise. Why?
It's a balance. Too shallow, and the water seal can easily get sucked out, that's called siphonage, letting sewer gas in. Too deep, and it doesn't clean itself properly, it collects debris. So that 2 to 4 inch range is kind of the sweet spot for performance.
Incredible detail. Okay, so gravity handles the drainage going down, but how on earth do you get water up? Say to the top floor of a really tall skyscraper, like 60 floors up. Street pressure won't cut it, surely.
Absolutely not. No way. This is where pressure management becomes a huge, complex engineering challenge. In very tall buildings, you just can't use a single pressure system fed directly from the street main. The pressure needed to get water to the top floors would be enormous at the bottom, like dangerously high. It would burst pipes, blow out faucet washers,
Okay, yeah, that sounds bad.
and conversely, the top floors wouldn't get enough pressure, maybe just a trickle. So the solution, the standard engineering approach, is called zoning. You divide the building vertically into zones, and each zone gets its water from dedicated tanks, often elevated tanks placed at different levels within the building. These might be fed by lower suction tanks and pumps.
So you have tanks inside the building at different heights.
Exactly. Our source material shows an example like a 64-story building. It might be split into, say, 3 or 4 zones. Without zoning, if you look at the numbers, fixtures on the very first floor could be under something like 149 psi of static pressure.
149 psi,
Yeah.
that's huge, isn't it? Like, what's a car tire? 30-something?
Right, around 30, 35 psi. So 149 is massive pressure. That's why even within a zone, you absolutely need pressure-reducing valves or PRVs installed on the lower floors of that zone. They throttle the pressure down to a safe, usable level, maybe 50, 80 psi, for the actual sinks and toilets.
That makes so much sense. Zoning manages the pressure. What about the actual pipes carrying all this water? Does zoning affect the pipe choices too?
It does, indirectly. Zoning helps minimize issues like pipe expansion and contraction from temperature changes because the pressure variations aren't as extreme over the entire building height. It also means engineers can often use smaller, more manageable pipe sizes within each zone instead of needing gigantic pipes running all the way up the building. That saves space, saves cost. As for the pipe material itself, well, engineers choose from things like steel, cast iron, copper, various plastics, brass. Depends on the water type, hot, cold, waste, budget, local codes.
And does the material affect how it's installed? Like overhead versus hidden?
Definitely. And crucially, how it needs to be supported. For instance, plastic pipes are much more flexible than metal ones. So plastic PEX systems need supports much closer together to prevent sagging over time. Our source shows examples maybe just simple metal straps nailed to wooden joists if it's in a ceiling space. Metal pipes, being more rigid, can span longer distances between supports.
Okay, this is where it gets really interesting to me. The idea of pipes not just being overhead or underground, but sometimes being hidden within the building structure. The source had a great example. Horizontal waste piping above the structural slab in a concrete office building. How does that work?
Yeah, that's a clever approach, often used in commercial buildings. Instead of hanging the waste pipes below the concrete floor slab, you actually run them on top of the structural slab. So the pipes carrying waste away from toilets, floor drains, etc., they run horizontally across the concrete. But then, of course, you need to cover them up to create a level floor finish.
Right, you can't just leave pipes exposed on the floor.
Exactly. So this method requires adding a fill, usually concrete or sometimes a lighter material, typically about 5 or 6 inches, maybe 125 to 150 millimeters deep, over the pipes. This covers everything and gives you a surface for your final flooring, like tile or carpet. The trade-off, it directly impacts the finished floor height. You lose 5, 6 inches of ceiling height below, or the whole building has to be designed slightly taller from the start. It needs careful planning between the architects and engineers right from the beginning.
So you're trading ceiling height or overall building height for concealed pipes within the floor structure. Okay, now it's not just liquids and wires and pipes. Air flows through them too.
Yeah.
Tell us about things like earth tubes and underfloor air supply. How do they fit into this overhead underground within structure picture?
Earth tubes are a really neat example of using underground piping for essentially passive climate control. It leverages the stable temperature of the earth a few feet down. They're basically just long pipes buried underground. A fan pulls outdoor air through these pipes. As the air travels through, the surrounding earth naturally cools it down in the summer or warms it up a bit in the winter before it even enters the building's main HVAC system.
Wow, so literally using underground pipes for a kind of natural pre-air conditioning and preheating.
Exactly that. It's a low-energy strategy. Then there's underfloor air distribution, or UFAD. This is becoming quite popular, especially in modern open-plan offices. Instead of blowing conditioned air down from ceiling ducts, like in most older buildings.
Right, the traditional way.
With UFAD, the supply air, which is usually cooled just a little below room temperature, is gently introduced through outlets in the floor, often swirl diffusers, at a low velocity.
So the air comes up from the floor instead of down from the ceiling. Why do that? What's the advantage?
The main arguments are better indoor air quality and improved thermal comfort. The idea is that heat naturally rises, right? So you introduce the cooler, fresher air low down near the occupants. It gently pushes the warmer, potentially stale air upwards towards the ceiling, where it can be returned or exhausted, creates a fresher breathing zone around people's desks. But there's a structural implication.
Ah, okay. What's the catch?
Well, this system relies on using the space under a raised access floor as the air supply duct. This space is called a plenum, so you have to build a raised floor, maybe 6, 12, even 18 inches above the structural slab. And that entire void beneath becomes the pathway for the air. While it offers benefits, it means you need greatly increased duct sizes, or rather, this large underfloor plenum space. It's a significant within-structure space commitment. It impacts floor-to-ceiling heights, requires careful sealing. It's a major design decision.
Got it. So a different way of hiding the ductwork,
Right.
but it takes up significant vertical space within the floor assembly itself. Okay, so we've looked at electrical, water, drainage, air. Zooming out now, what are the big universal things engineers always have to wrestle with when they're choosing overhead, underground, within the structure? Let's talk access, insulation, maintenance.
Absolutely. Access is huge. You've got to think, how easy is it going to be to get to this system later on? Because things will need maintenance, repair, or maybe even replacement eventually. Think back to the underground electrical. Using those raceways or ducts instead of just burying the cable directly, that's all about future access. You can pull old wires out, pull new ones in without massive excavation.
Right, you don't have to dig up the whole street again.
Exactly. Compare that to the waste pipes buried in that 5-6 inch fill above the slab we discussed. If there's a leak or a serious blockage there, getting to that pipe means breaking up the finished floor, potentially jackhammering concrete. It's messy, disruptive, expensive. Much harder than accessing an exposed pipe hanging in a basement ceiling, for example.
So easier access often means it's less hidden, maybe less aesthetically pleasing, or requires different structural approaches like that raised floor. There's always a trade-off. What about insulation?
Insulation is critical pretty much everywhere, especially for anything carrying hot or cold fluids or air. Hot water pipes, cold water pipes, air conditioning ducts. Doesn't matter if they're overhead, underground, or in a wall, you need to minimize energy loss. Our sources talk about using materials with dead air spaces or reflective surfaces, things like fiberglass, foam plastics. And a key challenge, especially for pipes within structures, is avoiding thermal bridging.
Thermal bridging, what's that?
That's where something conductive, like a metal stud in a wall or even the pipe supports themselves, creates a pathway for heat to bypass the insulation. So you can have great insulation on the pipe, but if it's clamped directly to a cold metal beam, heat will just conduct right through the clamp and beam, defeating the purpose. You lose energy. It needs careful detailing during installation.
Ah, okay. So even how you attach the pipe matters for insulation performance. Makes sense. And finally, maintenance. The ongoing reality.
The ongoing reality, exactly. It touches everything we've discussed. Those self-cleaning traps for drainage. That's about minimizing maintenance needs through good initial design. The fact that plastic pipes need more supports than metal. That's about ensuring longevity and preventing future maintenance issues caused by sagging or pooling. And think about those complex zoned water systems in skyscrapers.
With all the tanks and pressure valves.
Right, they have lots of components. Pumps, tanks, those pressure-reducing valves, maybe expansion chambers to prevent water hammer. Water hammer is that banging noise you sometimes hear when a valve closes suddenly, causing a shock wave. These systems need expansion tanks to absorb that shock. All these components require a regular planned maintenance program to keep working correctly. If not, you get leaks, pressure problems, failures. The accessibility we talked about directly impacts how easy and therefore how costly that maintenance is.
So tying it all together for everyone listening, what's the big takeaway here?
I think it means the next time you walk into any building, maybe take a second to appreciate the invisible engineering that's happening all around you, below your feet, above your head, inside the walls. It's this incredibly complex network, fruit of countless decisions balancing function, cost, and longevity.
Yeah, the choice between overhead, underground, or within structure systems isn't arbitrary at all. It really showcases that intricate balancing act designers perform efficiency, accessibility, upfront cost versus long-term cost, safety, environmental impact.
These are foundational decisions. They literally shape how a building feels, how it performs, how safe it is, how sustainable it is. They make our built environment work.
And it's just a great reminder that sometimes the most effective design, the most critical engineering, is the stuff you don't see, the hidden systems quietly doing their job. Maybe the thought to leave you with is this. As materials get smarter, as we develop more advanced sensors and maybe AI-driven building management, how might those future technologies change this balance? Could we see systems that are even more integrated, more hidden, yet somehow easier to monitor and maintain? What's the next step in this evolution of hiding the essential arteries of our buildings?